Hello, this is Geoffrey Fox discussing in the second slide deck work of his research group in Cyberinfrastructure, Clouds, HPC, and this one has a special focus on edge computing, but also quite a bit on back-end HPC and clouds. This is sort of our current active research. All right, so this describes the sort of abstract of this talk. And we're looking at simultaneously at the integration between simulations and big data. That's not discussed much in this talk. It was discussed at greater length in the previous talk, divided into three parts, and I have other talks describing in even more detail. The other convergence is HPC, cloud, and edge convergence, which is a major industry focus at the moment. They need HPC with clouds to do data analytics. They need edge and clouds so the clouds can support the Internet of Things. So we need to, we believe these two convergences are very important, and we're trying to combine both of them in our current work. And it's because this way will give the most convenient, broad computing environment, which will sort of stay okay even as these various trends go back and forth. Okay, so we look at these trends today. We had some trends from 2011 in the previous talk, part 2. We see data getting more important than simulations. We see actually as data gets more sophisticated and larger, the actual analysis techniques are changing. You go from older, rather simpler analysis methods to a newer, more sophisticated analysis with greater emphasis on machine learning and deep learning. Although everything is increasing in importance, data is actually increasing probably more than the simulations. A particular aspect of the data growth is edge computing, which is basically the computing model, the IO, or might call it even the Internet of Things software platform. That's what Gartner calls it on the hype curve, which is where it exists. And it is growing in importance. The Exascale initiative, which is the sort of supercomputer driving force, is building better and bigger supercomputers. And as we stressed, is aiming at a different type of application, although those machines and that software could be very valuable. An interesting trend is the growing use of public clouds. That's partly because the clouds are actually getting more and more powerful. They have much greater capability. They used to be relatively low-end commodity systems. Now they have high-end capabilities. They have GPUs, FPGAs, high-performance networks, lots of storage, lots of memory, and so on. And they have, as we stressed in the earlier talk, economies of scale, which makes them hard to compete with. A new development, which we'll stress, is serverless computing, which is, for trivial reasons, attractive to the user, because it's sort of clear that having no server makes it easier to manage than anything else. No server is easier to manage than no server. All right. All right, here is a nice picture. Well, maybe it's not nice. It's my favorite picture of describing two concepts, serverless computing and event-driven computing. These are often juxtaposed because the same software that does event-driven computing tends to do serverless computing, such as Amazon Lambda and IBM OpenWhisk. This picture here sort of comes from IBM, and it has peer-to-peer, an example of true serverless computing. What you get in event-driven is server-hidden computing. Event-driven includes function of a service, or often microservice as a service. Functions tend to be small microservices. It is supported by multiple projects, Open Lambda from Wisconsin, OpenWhisk, IBM, Amazon's Lambda, Google's Cloud Functions, Azure Functions are the three big commercial projects. So this is function of a service, and it is supported by serverless computing, which is provided by the owner of the cloud. Maybe Amazon does the work to provide serverless computing. IBM does the work to provide OpenWhisk on the IBM Bluemix platform. It's cloud native. It supports applications optimized for the cloud. Currently, it does short-running stateless computation. It is expected that these characteristics will be removed. They are event-driven. An event happens, it pokes the function, and the function is launched. It scales up and down, it's intrinsically elastic, and it only charges for actual time use, whereas Amazon and infrastructure as a service, if you finish your job but don't switch it off, then you still get charged. So this sort of shows how serverless builds on all previous ideas. Bare metal is the basic, infrastructure as a service, platform as a service, containers and orchestrators, and then on top of everything, and the most elegant is serverless. And obviously users like that best. We have a review on the internet of serverless computing, and I recommend you look at that. Another set of important trends, which we've again effectively discussed in the earlier talks, that HPC is critical for parallel computing. Apache is giving you these wonderful Apache big data stack. It has some edge computing capabilities such as Storm and Heron. We pointed out the differences between parallel and distributed computing, and that we didn't mention the Apache stack typically uses distributed computing concept, and therefore it does a different reduce operation from that present in MPI or our system from Judy Chu HARP, and that's different from what Spark uses and Flink. If you look at big data requirements, there's probably no real consensus, but there are some key use types. Pleasingly parallel, so-called local machine learning. You do the same thing on lots of different events. The database model with queries supported by MapReduce for horizontal scaling. Global machine learning, where you take a single job like Dirichlet allocation or deep learning or clustering, which uses multiple nodes in classical parallel computing style. And here our part 4 is deep learning itself, which is a subset of global machine learning. If you look at most workloads, I think they're dominated by 1 and 2, and 3 and 4 are of growing importance, but still relatively modest. And Spark does badly on 3 and 4, but is hugely successful because it supports 1 and 2 extremely well. You can't draw conclusions from current successes unless you look at the applications they're running, and they have features. So supercomputers are going to be essential for doing the large-scale, major, nationally critical simulations for nuclear stockpile stewardship, new materials, and so on. However, I think the most important systems for most people will be HPC clouds, or what I can call next-generation commodity systems, which merge cloud, HPC, and then with clouds, they have the support of edge computing. These clouds will run in giant data centers. I've stressed how those offer economies of scale, and they offer everything. We will have distributed data sources associated with devices, and there'll be fog processing. This is computing near the devices. We have a device fog cloud model. We have server hidden or serverless computing for the pleasure of the user. The user doesn't want to mess around with the details of the cloud. So we have to support a distributed, event-driven, because the edge is all event, serverless to make it nice for the user, data flow computing model. And it needs to do batch and streaming data. And it needs to merge parallel and distributed and grid computing ideas. And this spans pleasingly parallel to data management, that's databases, to global machine learning. That's what we're trying to do. All right. If we look at these convergence points for these different ways of doing computing, we have applications where we've already pointed out that you need to divide into data and model and talk separately about the data and model. And we have these convergence diamonds or ogres, which describe that. We have the software with HPC, ABDS, and 21 layers, giving high performance runtime to Apache systems. So the Hadoop runs fast using Judy Chu's HARP plugin. We have general principles that get good performance from Java or C as the programming language. On the hardware, we're going to use serverless as the infrastructure for services or microservices. We're going to use DevOps to automate the deployment of event-driven software defined defined by configuration files, and they'll be deployed on hardware that is designed for the needed functionality and performance. They have the right disks, interconnect, and memory. And then, of course, we use the concept of HPC Cloud 3.0. We're delivering solutions as a service, or wisdom as a service. Cognitive computing, as they tend to say in IBM. All right, that's all of it. We build around this NSF project, which developed the ogres. The ogres were actually originally designed in the proposal for this project. It builds HARP and now Twister-II. HARP is the parallel computing a global machine learning system, and Twister-II, the distributed edge computing environment. Those are building blocks. And you have the Spiral data analytics library. And this shows you that the blocks, ogres, the Spiral library. Midas is the middleware, including HARP, Twister-II, pilot jobs. And then we have HPC, ABDS, the core software stack we're building on. We have applications in network science, biomolecular, polar science, and pathology. And then we have all our collaborators: Stony Brook, Rutgers, Kansas, Arizona State, Utah, and Virginia Tech. There we are. Here is this other way of looking at it, which I actually presented earlier, built around this graph from Google, which has as a function of time the amazing inventions, starting with Google File System, and then perhaps most importantly, MapReduce, HBase or Big Table, that's the NoSQL, initial NoSQL database, Dremel, which is Apache Drill, which is a SQL interface to unstructured data, Pragle for graph processing, probably superseded by later developments by the various data analytics initiatives. Flume Java, which is Apache Crunch, is an orchestration system or high-level programming language. Colossus is the better global file system. Spanner is the better NewSQL database, combining SQL with as the query language with a back-end, more scalable approach. And then Millwheel is Google's alternative to Storm or Kinesis. And here we have Cloud Data Flow, which sort of supersedes Dremel. And then, as we've noted, there's some things they don't discuss: security, data transfer, scheduling, DevOps, serverless, and where, of course, Apache OpenWhisk is the contributor. But I think this gives a very good, I mean, these are probably highlights where they have really seminal papers, and they did very clearly the first work. Millwheel's perhaps the only case where they went first of this in this set. But it's a sufficiently large fraction of the important software that really highlights the amazing progress in software systems in the big data stack. Okay, here we have this slide I've shown before, the 350 HPC ABDS software systems, which basically combine HPC and Apache Big Data Stack. I gave up improving it in January 2016, there are probably another 50 to 100 entries over that today. And its main thing is to notice the number of layers. These layers, I believe, are reasonably well thought through, although they're a bit messed up because I split layer 15 into two. So I didn't get it quite right initially. There are 21, even though it's from 1 to 17. That's 2 with 2 parts and 1 with 3 parts. And the 11 is file management, NoSQL, and SQL for the database data management approach. So we have 21 layers, which I think is sort of roughly right. Google had about half of that in their highlights, but you need these other layers. You need security, you need monitoring, and so on. And they just didn't have seminal papers in some of these areas. So this is what you're building on. We know it's very important to exploit this. All right. Here we have just a highlight of the so-called convergent diamonds. There are 64 of these things here, arranged in 4 views. There's one view here, the processing view. The data source and style view is here. It describes how the data is processed and stored and accessed. The execution view has things like size, model size, data volume, some core low-level characteristics of the system and the algorithms, like whether it's iterative or not, whether it's metric space or not, and things like that. And over here, we finally have the problem architecture, which is this is the microstructure, this is the macrostructure, the overall structure of the system. And that system can be thought of as either the software or the application, because you build software to match the application. Actually, hopefully, it matches the hardware. Otherwise, you won't get good performance. In this analysis of 51 use cases, 41 were streaming, 26 had major pleasingly parallel parts, and 25 had map-reduced-like parts. I've seen this graph before. It actually fits better on this form factor. 6 computational paradigms for data analytics. Map only, classic map reduce, iterative map reduce, or map collective. This is classic big data. The classic simulation or classic graph is point-to-point or map communication. The critical data streaming architecture is map streaming, maps running all along here permanently, and data streaming in from the side, buffered in brokers. The 6th thing is the shared memory needed to get decent performance on some graph algorithms. Twister 2 is focusing on these 3, because the other 2, which are done well in Spark and Flink, sort of follow automatically if you can do these 3 harder ones well. All right, so in this slide, we highlight the well-known Mahout library, which was originally built for Hadoop. And then Spark and Flink have shown that it's really not very satisfactory. But that was known, in fact, was pointed out by Twister first, that anything built around writing to disk with the reduction operation is bound to get poor performance. But even MLlib, which is Spark's library, is not very high performance, as we'll discuss later on, because they're using non-optimal communication models. Spiral has then the equivalent of Mahout's with high performance plus various community algorithms for biomolecular simulation, network science, and image processing in a variety of cases, including pathology and polar science. Here is the Spiral core library. It actually lists the library members, such as deterministic annealing, multidimensional scaling. Then it follows by the collectives. I stressed to you earlier that machine learning uses collective communication because it doesn't have the nearest neighbor structure, which leads to different communication structures for graph algorithms and for simulations. These deterministic annealing, multidimensional scaling is probably the best MDS, which is dimensional reduction algorithm there is. It's very, very robust algorithm. This is for the general case where there are no vectors defined in the problem. If there are vectors, we have different algorithms. Here we have a clustering algorithm of vectors, deterministic leading vector sponge, which was originally produced for a proteomics problem, and it uses slightly different collectives. The basic order n squared, so-called symmetric clustering, that's when it's you have a distance defined, but not vectors. That uses yet slightly different collectives. And anyway, so here we have a list of quite a lot, over 20 library members and their collectives, trying to show how that this model of map collective makes sense. Notice a lot of these have been optimized with the Intel data analytics library on the node. This is a node optimization, not parallelism between nodes. And Judy Chu's group has put that into a lot of these algorithms. All right, now we come to a new section discussing Twister-II in detail. And this sort of defines for the first time the fog in a clear fashion. We have in the center HPC clouds. We have on the edge all the Internet of Things, the 20 billion things sitting there. And we have on the right the correct architecture, which has fog, which is computing near the things. They could be on the things or on something attached to the things, like we have a car with, say, 100 sensors, 100 things on it. They could have a built-in computer, a GPU to do deep learning or something. And that it would be the fog. It will be solely in the car and devoted to the things within the car. The model of a fog, whether it is closely associated with the devices or on the device, like on the robot, is not well understood, or there is no consensus. Because in the simplest case, like your Alexa, Amazon, Echo, and things like that, everything is essentially done on the cloud. So if you have dumb devices and cases where you don't mind the second or so latency it takes to go to the cloud, well, it doesn't have to be a second, but it would be hundreds of milliseconds, then you do not need the fog. The fog is essential if you have to do, say, real-time processing to avoid your car colliding with another car. All right, so I do Twister-II because Twister was pretty successful. It has 878 citations. It was, if you like, it was actually slightly before Spark, but it came out roughly at the same time. And it introduced for the first time map collective iterative processing. And the key idea with Twister-II, which sort of builds on all our experience, which is quite extensive now, on Spark and Flink and Twister and Harp and things, the aim is to re-engineer all these systems as a toolkit, namely to try to break them up into parts, because the trouble is they put together particular parts, and sometimes those parts aren't the best part for a particular problem. And we think it would be good to have a toolkit so I can choose the right part, so I can grab the right part for my problem. And it's meant to do this. So serverless, by definition, cloud native, data flow, event-driven, microservice-based, function as a service compute model. And it's running across geographical domains as it goes from edge to cloud and different applications. And it will do global machine learning and edge computing. And it tries to build on the best practice of the cloud, but in the spirit of HPC ABDS, use HPC wherever possible to get high performance. And it's meant to somehow bring together Spark, Flink, Heron, MPI, Dharma, which is a exascale type software environment, and Hadoop. And it has this idea of polymorphism. And we have multiple implementations of each part of the toolkit. So you have different communication libraries, one for distributed data flow, one for in-place high performance, and so on. So you don't require one runtime, you require a set of common APIs and abstractions, but multiple implementations. Notice Twister-II is a runtime. but a given runtime suggests a programming and execution model. And some of these things are like event-driven, that you could view as a programming concept, because it's telling you you must post events to get anything to happen. And this, in some sense, is a next-generation grid, because it is doing distributed computing, but it's a grid based on data and edge devices, whereas the previous grid was built around distributed computing. And we have a paper here with a link describing Twister 2. Twister 2 is meant to have something significant happening in January. All right, so we've decided what the idea is. Event-driven functions. Each of those is a microservice. So we don't want to have libraries, which is sort of the common approach for a classic processing. You have your machine learning library. You put it in /user/bin/lib, and then you invoke it. No, we want to have each of those library members to be a function, a microservice, and you can invoke them with an event. There are some important issues about state, which I pointed out. The serverless is currently stateless, but for sophisticated applications, you really need state. And that will be done outside the frame by allowing yourself to store things and access storage and things like that. You will have all the features of iterative MapReduce built into Twister and Spark and Flink. And these functions can be individual functions, sequential, or as in the spirit of the challenge of Roger Barget at the serverless workshop of running 100,000 simultaneous synchronized maps. We're assuming that we run in HPC clouds, not clouds, just HPC clouds. I mean, we're assuming that if we run in an HPC enhanced cloud, we can also run in a cloud by not using the enhancements. We want to run in the fog or the device. And a sort of thing to look about is Amazon Greengrass. That is Amazon Lambda running on the device. Notice that we can sort of have a hierarchical architecture. If you're a web sensor, if you're a sensor on a car, say a LiDAR or something, then the car's computer, the centralized car computer, is the fog, and it looks like the cloud of the device. You can access that fog as though it was a cloud. It just happens to be nearer. And the public cloud, which is a long way away, looks like a cloud to the fog. So we have a hierarchical system. Device goes to fog, thinking it's a cloud. Fog goes to cloud, thinking it's a cloud. And in principle, you could have that go on ad infinitum. So we need to look at the existing systems. We haven't totally finished this. I noticed Naiad has the best logo over here. It's a nice Greek goddess. And it was a system coming from Microsoft, which was aimed at timely data flow. And it was long-running tasks that executed large data flow applications efficiently. Then we have Spark, Flink, Naiad, Hadoop, Storm, Heron, which are streaming data flow, workflow systems, Kepler, Pegasus, NiFi, HARP, which is Judy's map collective model, MPI, the asynchronous many-task runtimes from high-performance computing, which are Dharma. And then we need to look at grid FTP, Corba, high-level architecture, because those also have communication models. So we're trying to look at the combined HPC, cloud, big data world to extract the good ideas that we can then steal, or not steal, we can then study and see how they should be placed in our toolkit. Here are some motivating work we did comparing Spark, Flink, and MPI. And this is on so-called global machine learning. And notice we've already stressed this is not the dominant application for Spark and Flink. So Spark and Flink don't look so good here. But that's because they're not used here. It's fine. They're used in other applications very successfully. Pleasingly parallel, MapReduce. So we did a study where we looked carefully at 3 applications: multidimensional scaling, TerraSort and K-means. We wrote everything in Java, and then we run it on these 3 environments: MPI, Spark, and Flink, where the MPI is OpenMPI, written in C, and wrapped to run as Java. And one key observation we'd made actually a while ago was, why does Spark and Flink not work well? Well, they use reduction, which is needed in all these applications, or at least it's needed in MDS and clustering. When Spark does a reduction, it does this. It spawns all sorts of tasks. It doesn't actually have an all reduce built in. It has to do a reduction and then a broadcast. So that's pretty messy. As MPI has these continuously running processes or tasks, and it does everything in place. They just have a beautiful, elegant, coordinated communication exchange which implements all reduce. And it's just much faster. It's not having the overhead of invoking tasks, and it's actually more efficient. And it also does all reduce in the same time as doing reduce. Whereas in Spark and Flink, you have to do the broadcast to get all reduce. So, of course, we haven't even discussed the dupe, which is much worse. It actually writes the disk instead of these elegant communications. Notice this model here is more fragile. If anything breaks, we're in trouble, because those communications are all carefully arranged to be optimized and get the right answer. But if one of them goes wrong, we're doomed. So here are some typical results. This is the MDS logic. And here we show Flink, which is the top, then Spark, and then MPI. MPI has 2 curves. One is the compute part, and the other has communication. The compute totally dominates. There's tiny communication. But it's actually the reason why Flink and Spark are so bad is because of communication. And you can see they're sort of almost 2 orders of magnitude worse for Flink, and almost over a factor of 10 bad for Spark. And it's worse, not surprisingly, for small problems. All overheads are worse as this problem gets smaller. So this is 16 nodes with a fixed number of 20 processors in each node and varying number of points. Here we have 32,000 points, this one here, on varying numbers of nodes. And we're comparing, this is again a logarithmic plot. And here's here's 16, which we showed here. This one is 16 nodes. Here we actually go up to 32. And of course, for 32, MPI is running faster than 16, as we hoped, by about a factor of 2, which is what you'd hope. Whereas Flink and Spark are running slower on 32 than 16. So there is no doubt that Spark and Flink just do not do this problem. If you look at one of the reasons is you have to draw the data flow graph in Flink, and here's the messy data flow graph. And Flink doesn't understand very well a key feature of the MDS problem, which is it has multiple nested parallelisms. And Flink gets lost and doesn't align properly the parallel compute and the corresponding data. And so it is particularly inefficient. Spark does not get lost, but it uses these incorrect communication primitives, and that is one reason it runs slow. All right, TerraSort. This is sort of a classic big data. It's not global machine learning. It's just effectively a data transfer problem. And here we have MPI with 2 models. We're using InfiniBand and using TCP/IP, which is, not surprisingly, the best result is 64 nodes, MPI using InfiniBand, by far. Well, if you do, so this shows a lot of the reasons that Spark and Flink are running slow is they're not using optimized network performance. This is a linear plot, so TerraSort, which is not iterative, does not have these disasters that MDS and actually clustering have, but it still shows clear better performance for MPI. Notice in this case, Flink is outperforming Spark. Here's Flink, 600. Spark is 1100, almost twice as much. All right. Now let's look at Twister 2 in a little more detail. By the way, we have other graphs like the clustering results for that thing which I didn't show, the k-means clustering. They're not as bad as MDS, but they're not good. MPI still works much better. All right, so what do we have to do for our distributed HPC function of a service framework? Well, we have to look at all these tools. The green things are what we're doing now. And we have to handle the events because we need to invoke them as event-driven computing. So we've got to be able to handle events. And we're doing that at the moment. We're not looking at state. I'll mention state a little further on. We have to do scheduling, and we have to invoke the functions. And we have to build these data flow graphs in an efficient fashion and analyze it. And then we need to build the graph and then execute it from this internal event-driven model. We need to worry about the geographical distribution so we can do device, fog, cloud. And we have to build the data flow collective and the peer-to-peer, which we will use HARP, where HARP is the best approach, which it is for global machine learning. And we will use other mechanisms where distributed computing ideas are better. We have to look at streaming. We're using Heron as our initial framework to modify. So we're starting with Heron, which of course has built-in streaming. We need to build an in-memory data set, which is sort of like what's called RDD in Spark, and we have to be able to back that up. So we expect to use some variant of RDD. Spark has done a great job there, and one of its great successes. We should try to exploit that, and so it will give us the same fault tolerance Spark has. We need to have the DevOps to invoke it and the server hidden cloud models, and we need to have elastic function as a service. So these are the things in black are to be done. The things in green are in process, but they're not so far along. Let's just look at communication. We can actually compare 4 different communication models. MPI, tightly synchronized microsecond latency. Data flow, you model the computation as a graph, and you implement it as that graph. And it's all data flow and data driven. So it's a very elegant, fault tolerant, easy to distribute model, but it's slow when you can actually use the in-place MPI model. Streaming data flow, when you have streams, which are when you partition the data into streams. And the order of events is important, and you have to group the data into time windows. That's a classic problem done in the streaming systems. Then we have to look at machine learning, which is iterative, and we have to keep track of state. There's model and data, but you only communicate model values, not data values. And you have these collective communications. And we know that in many cases, in-place MPI is the right approach. Here is a data flow graph to illustrate basic data flow. I showed you a complex data flow for MDS and Flink. Here's another example of looking at collectives. We have various collectives listed here for MPI and for big data. And here are various algorithms for implementation. Notice, depending on the exact value of network performance and problem size, number of nodes, different algorithms are better than others. So you can either use trees to do, say, broadcasts, or you can use pipelines to do broadcasts. And that's been known now for, I remember working on that in the early 1980s. And many PhD students have written beautiful theses on the best way to do different collectives. But all that work's been done, as far as I know, for the HPC applications. It has not got a lot of attention for these big data flow problems. So one of the things we're trying to do is look a little more carefully at this work to see the best way to do it. All right, so this Judy Chu in her presentation will describe in more detail. HARP is a wonderful technology, especially to support DAAL, the Intel Data Analytics Library, and it is the Digital Science Center or the Indiana approach to doing global machine learning, and it basically was she invented the map collective model, and there was although it was still the present, if you like, in earlier work, but it wasn't identified as a key idea, the difference between map reduce and map collective. And here we have HARP built into Hadoop, MapReduce version 2. Yarn is the scheduler, and you can run MapReduce or map collective applications. And HARP has got its communication optimized for various algorithms. The most sophisticated work is done on latent Richelieu allocation. If you go to the Digital Science Center publications list, you will see that work on that website. Let's look at state. State is pretty interesting. And it's handled differently in different systems because you have, say, in some problems, you have long-running tasks. Like MPI is long-running. Storm and Heron is long-running. Spark and Flink, on the other hand, stop at the data flow node. There they write the RDD, possibly in-memory data set, and it changes. State is lost. Start again. And notice that really the only issue is the grain size. If you do coarse grains, as you do, say, in workflow, everybody agrees that you stop at the data flow nodes. But in k-means or MDS, you are looking at fine-grained data flow. It is not at all clear. In fact, I think it's certain you shouldn't stop at those data flow nodes. At least if whatever you do, it should be very lightweight. Because if you stop at those iterative data flow nodes, it will be very slow. We have various approaches to scheduling. Notice Spark is dynamic scheduling, and Flink is static scheduling. And that is sort of related to the way they think. Flink does a lot of work on query optimization, so it needs to be done statically, whereas Spark is done dynamically with fine-grained control of the data flow graph. So you can't optimize it because it's you're not doing it as a static optimization. Fault tolerance. So we note that actually checkpointing is not different really in HPC and big data. The only issue is that for some reason HPC is rather informal on this checkpointing because it doesn't do it because really big data is very elegant. We have a data flow graph, we checkpoint at those data flow nodes. But HPC is actually identical. It just doesn't call it a data flow graph, and it doesn't say we checkpoint in memory databases. It just doesn't say that, whereas it could. And I think it's because Spark and Flink come from the database community and do a better job of that. MPI has a richer state than the model in Spark and Flink, but we can take that richer state and extend what Spark and Flink do to the richer state. So I think there's a good way to merge MPI, Spark and Flink, and RDD as a checkpointing and state model. One thing we want to do, which is very important, is you don't want to checkpoint every iteration. You probably only want to checkpoint every 50 iterations, because you don't want to spend more time checkpointing than you do iterating. So you need to choose the iterations, the checkpointing intervals, so that the overhead due to checkpointing is small. That's a very simple thing as far as I can see to do. Here is now a little discussion of how things look in, say, Spark. Here we have a Spark k-means data flow specified. Here is actually in Flink. And this step here, which calculates the centers with a global reduction, it stores those centers in an RDD. So we want to sort of think of MPI and global machine learning in this fashion, but not implement it in this distributed data flow fashion. All right, so we're nearing the end of Twister 2. So this repeats what I said before. We are suggesting an event-driven computing model. It's built around cloud and HPC. It spans batch, streaming, and edge. It's highly parallel in the cloud. It's possibly sequential at the edge. It's using microservice as a service or function as a service and the serverless or server-hidden computing model. We have a high-performance data analysis library, which we can put into the function of a service. We've integrated HPC into lots of Apache systems. And we've done a preliminary analysis of the different runtimes from Hadoop, Spark, Flink, Storm, Heron, Naiad, Dharma. And we want to make this polymorphic. And we're still working on state and other issues to try to get it right. And here's this paper again, the Twister 2 paper with me and Supin.